Good morning. This is Mr. Weiss, and this is 7D Physics. And I got a couple folks already, so welcome and say hello. And I'll get that so you can see the whiteboard for later. And once I get a bunch of you here, we're going to start up. So nice to have you guys there. Let's see who's here today. So say hello. I've got 4 of you, and we can see who that is. Why am I looking fuzzy? Hopefully that will become less fuzzy. I've got Marino. Good morning. I've got Stephanie. Good morning to you. Lisa's here. And I guess that's it. I had 4, now I have 3. So I have you 3, that's great. We're going to look at some definitions in English and German today. Even if I'm out of focus, I'm not quite sure why. Maybe it's my camera. You can still see the board, and that's the important thing because we're going to write up some terms in English and German today and learn stuff in both languages that we need to know for next year. And I got somebody else. Tully's here. Very good. Hope you guys are well. We got a couple weeks of school yet, and that's about it. We're running out of year, even though it's been a crazy one, huh? UCN is here. Good morning. Looks like I got somebody else. Let's see, how many did we get last time? We had a lot of you last time. Maybe we'll get a few more today. Got 5 so far. That's a good start. I think is it you or 8th grade next week? I think I might see some of you at school next week. I'll be there several times, so maybe at least enough to say hello. I don't know if I teach you science again or not. I think you go in next time if I'm right for your English classes, so you might be kind of mixed up. Okay, well, let's go ahead and begin. And again, I'll move that up a tiny bit. You can see the whiteboard. Okay, as folks arrive, I'll just check them in as per usual. Let's get some review from you first, okay? So, what are the 3 phases of matter? Hello, Tilly. The 3 phases of matter. Just type it in, just so we know what we're talking about. In German, it's Aggregatzustand. Solid, liquid, and gas. Tully is quick on the draw. She is right. We're going to focus in on some phase changes today. I know you and I acted out this, and a couple others joined her and answers. Good. I know we acted out this at the beginning of the semester in the before Corona time. And we want to get some terms straight today. Oh, everybody's got it. That's cool. Well done. Well done, everybody. Yeah, let's go ahead and begin. I want to talk about this term first. You probably know what it is. And it's in English, evaporation. Evaporation, okay? And in German, it's verdunsten. Let me check my other board or my other website and make sure I have the word spelled right. Verdunsten. Yes, verdunsten. No, I don't. It's a good thing I looked, huh? I don't want to teach you bad German. Verdunsten. Okay, let's see if anybody else showed up. I got 7. 1, 2, 3, 4, 5, 6. I got a 7th person. Say hello so I know who you're at. When a liquid becomes a gas, right? Exactly. And it really is any surface. Okay, so let's just take a puddle. right? And a pfütze. So there's a puddle, right? Not a poodle, a puddle. So there's some water because it's raining today anyway. Good day to talk about this. And I've got some molecules. Remember how we're moving chaotically. So there's some molecules going slow, some faster, even in the liquid here, okay? So some are going fast enough to leave. Woo, and away they go, okay? Some particles can leave. Now, a few may join the puddle as well, by the way. But mainly I'm talking about those that leave. Okay, evaporation are these guys, okay? See if you can see that. See that okay? Evaporation are the guys that are leaving some sort of liquid. Emelina's here, good. Thanks for joining us, everybody. So evaporation, so these are when we got particles in a liquid going fast enough to escape. It really is sort of like that. You'll see why in 10th grade, to escape and become a gas. And I'm going to tip that so I can make sure you see it all. I'm going to read it again for you. So evaporation, Verdunstung, particles in a liquid going fast enough to escape and become a gas. Righto. I want to have you do something weird, maybe, that you get to do an at-home experiment. Ready? Okay, so take your hand, lick it, and then blow on it. How does it feel? Lick your hand and blow on it. How does it feel? Not salty, not how it tastes, but how does it feel? And I got another person here, so let me know who you are. Say hello. It feels cold. Exactly right, Marino. We're going to see why that is. Yeah, good. A lot of you got it. So why is that? Okay, so remember with our puddle, we got some particles that are just naturally going faster and they escape and become a gas. When you lick your hand, yeah, exactly, Emelina. When you lick your hand, even already, if I just move it in the air, it also feels cool. So I'm not talking about just the blowing on it matters. Even if I move it, it feels cool. Well, it feels cool. I provided more area of liquid. Like probably there's a little bit of moisture on our skin all the time, probably, and some of that evaporates anyway. But when I put a lot on, when I lick my hand, then I got a lot more that is there on the surface. And suddenly, when molecules get going fast enough, they leave. And I want to consider with you what's going on. Okay, so when I blow on it, I'm giving more molecules some energy. I don't know, what am I doing? Oh, I remember what I'm doing. When I lick on it, I'm getting rid of those particles that are right close to the surface of the spit. I know that sounds weird. So right at the surface of the spit, there are some particles that by luck are moving faster. I blow on them and those suckers evaporate. They verdunsten, okay? Real quick. Right, let's talk about what that is. Okay, so there's a word I want you to know for next year. I might have taught it to you this year. I don't remember. We'll see. Or maybe Het Tesman taught it to you. So I'll just write here, blow on wet hand feels cold. No, I don't want to see what this is. Anyway, you got evaporation happening. By the way, who else is here? I got 9 of you. 1, 2, 3, 4, 5, 6, 7. 2 of you need to say hello so I know who you are. Okay, so evaporation. I'll just write here, blow on wet hand. Let's see if you can see that. So when I blow on wet hand, feels cold due to evaporation. And then why? So it feels cold with a wet hand, and I'm guessing that's Mick, if I remember his thing right. So I think Mick is here. Okay. All right, let's see why. I'm just going to tell you the word and let's see if you know it, okay? I don't remember if you learned it or not. Okay, evaporation is endothermic. Let's see if I taught you that. Who knows what endothermic is? Or you might have had it in another class, I suppose, but I can't remember if I taught you guys or not. Did I teach you what is endothermic? If not, we're going to learn it right now. But it has to do with this whole process of licking our hand and blowing on it and making evaporation happen. We're going to see the relation in just a second. So Tilly says, no, we haven't had endothermic. Okay, endothermic means to make something happen, in this case evaporation, I've got to put energy in. All right, endothermic it's the science way of saying any process that requires energy to happen. Oh man, I just put the wrong letters. So endothermic, any process that requires energy to happen. Okay. To make a short story long, which I am, if I have evaporation, I need to give energy to those particles. And so it's endothermic. They got to have enough energy to escape the puddle and become gas. And on my hand, the little water particles got to have enough energy to escape my hand and become a gas. Same thing, evaporation, okay? Whether it's on my wet hand or whether it's from a wet puddle, okay? So that's the same process. And I'm trying to think of how best to do this with you. Other endothermic processes. Okay, I want to tip that and make sure you guys can see it. And I'm going to take some of your examples, okay? So I'm going to see if you can read that. Okay, so endothermic, a process that requires energy to happen. And certainly evaporation requires energy, right, to make the molecules of gas. Can you think of some other processes that happen or things that you would do in your daily life or the kitchen or whatever that take energy, that require energy? So can you guys give me some other endothermic processes? And I'll wait for some of your answers. So type in some things. What's something you do or something you've seen that requires energy? Could be a one-word answer, it could be a several-word answer to describe it. Something that takes energy to make it happen. Things that you do. What would take energy, require energy? Give me something else that's endothermic. And while I'm waiting, I'm going to tell you how to remember it. Endo, energy enters the system. That's how I remember endothermic. It goes in, it enters to make something happen. All right, Tully has to go. Okay, farewell, Tully. That was a short time, but that's the way it goes. Okay, now I got some answers from you. Let's see. Melting ice cubes. Emelina, I like it. Cooking on a stove. Super. Melting a snowball when we had those. Heating, cooling things. We're going to find out which of those, Lisa, that is. Okay, melting is a really good one. Thank you, Emelina. So melting requires energy, whether it's ice cubes or a snowball or whatever. That's an endothermic process. Anything else you do? Cooking something, right? UCN, good. Cooking is endothermic. I have to turn on the stove, don't I, UCN? That's right. Cooking. See if there's any others that you come up with. That's pretty good. You guys are thinking good today. Well, here's another one you never thought about. At least I hope you're going to think about it. Another endothermic process is, you ready? Cleaning your room. Am I making a joke? Kinda and kinda not. To do it, don't you have to put in energy? So that's endothermic as well. Cleaning your room is an endothermic process. I'm going to tip that so you guys can see that. So we've got some examples from you and one from me. Melting, cooking, and cleaning up your room. Maybe it's a process you haven't done in a while, right? Okay. I'm going to change boards. I hope you've had time to write that. I'm not going to erase it in case you want to ask something, but we're going to go and do the opposite in a second. All right? Okay? All right, here we go. Board number 2. This one's broken, so I got to be careful with it. I know it fell down one too many times. A little heavier than the other one, the frickin' thing. Okay, so the opposite of endothermic is exothermic. That's an E. Exothermic. So exothermic is any process that gives off energy while it's happening. And by the way, the words in German are virtually identical. Okay, so I'm writing any process that gives off energy as it happens. I'll tip that in case you can't see it. No, I guess you can see it, all right. The blurry parts at the bottom. And back to you. Ba-da-ba-da. Start typing. Give me something that you know that gives off energy. Anything in your life or the universe or whatever, something that gives off energy. Could be something from biology. Okay, Marino writes the sun. Yeah, the sun shining gives off energy. You're going to learn how in 9th grade. So let's do some examples here. Big EX. I'll write from Marino, the sun, and I'll say shining. So we know what we're talking about. That is exothermic. Marino has it. Some other ones. Lighting a candle. Yes. Good, Emelina. A burning candle. Oh, and Frederica's here. Welcome, Frederica. Burning a candle definitely is exothermic. So thank you, Emelina. Yeah, gives off heat, doesn't it? A heating pad. Tilly, that's tough. A heating pad, but it doesn't work unless I plug it in. So I know it gives off heat to you, but also we have to put in heat. So that heating pad's kind of complicated. Lisa, lightning. Yes, and you'll learn about that next year, why that is. Yeah, we can add lightning. How about let's take a candle? Anything else you burn? Yeah, UCN, not just fire, but what is it that you're burning? Can you be a little more exact? What is it that you want to burn? What else would give off energy? For example, if I, do I have a piece of metal? If I try and light this metal on fire, that will not be exothermic. It will not give off energy. Metal, if I do whatever with it, it will not give off energy. So Stephanie has something, burning wood. Okay, so burning wood gives off heat. That's exothermic. So burning candle, I'll write here, or wood. Any other things people can think of? You'll have more of this in 8th grade. What else can we burn? Candle, wood. Society burns 2 other things to make energy. You know what they are? They're both exothermic and they're both kind of important. Give you a hint. Cars and furnace or height zone. What else can we burn? Something that would be exothermic. Anything else you can think of? I mean, that's okay, but just to kind of round this out. You got it. Lisa has it. So burning coal, we burn coal in a lot of the Berlin area to get electricity. You'll learn how in probably 9th grade. Yeah, so we burn coal. Burning coal gives off energy. It's exothermic, the process of burning it. And I mean the process. If the coal just sits there, it's not exothermic. It's got to be lit, okay? Just to be clear. The other thing is in cars, right? Gasoline, benzene, right? That, once it's burning, gives off energy. So that's an exothermic process, burning gasoline in a car. I won't write all those, but just so you know, huh? Okay, right. Good. I want to go back and fill in another couple of words, okay? All right. Remember we have this word, evaporation? I want to talk about a word that sounds really similar, but it's not the same, okay? Vaporization. Vaporization. And I'm going to go back and make sure I have the word correctly in German. I do. And that's their Dampfung. Okay? Dampf is just like steam, right? Dampf. So to make something into steam. Gas going to liquid, still the other way around, Marino. It's still liquid going to gas. So if I vaporize something, it means literally to turn it into a vapor. So let's say change liquid to gas is vaporization. Change a liquid to gas. What was I trying to say here? I'm losing my mind. A dump pump. By boom. So I want you to fill in the word. I'm getting near the shiny spot, aren't I? So I've written here vaporization or verdampfung. It means to change a liquid to a gas by what? So what's the process we're doing? Think of the kitchen. The kitchen, what's the process you're doing that is involved with vaporization? One word, you do it in the kitchen all the time. Heating, yain, can you be more specific? Heat, UCN, heat, Marino. This word starts with a B. Cooking would be more like, Emelina, the German word, kochen. What's the English word for it? Burning, well, we're not really burning it, Tilly, okay? We're taking a liquid. If we burn it, that's like gasoline, but that's not the same thing. Oh, now we got it. Good. A bunch of people got it. Emelina, Marino. So boiling. Boiling. Okay. Boiling is different than evaporation. Here's my beaker. For boiling, and I know I'm getting to the shiny part. I'll try and write carefully so you can see it, and I'll tip the board in a second. Right, now several of you got it. Okay, so remember the puddle? Remember with the puddle how the molecules leave only right at the top, right? Okay, here's the secret. Boiling is different because now, you ever watch something boil? It doesn't just happen at the top, does it? I can form gas bubbles inside too. And then they go up to the top, I know, right? They're moving up here. And I can form them at the top, so I can have particles at the top leaving as well. So boiling is very different. Well, not very different, but it's different because I can have liquid going to gas within the liquid as well as above it. So that's boiling. So boiling. And I'm going to say here particles change L to G. I hope you'll know that that's liquid to gas. Hopefully. Particles change liquid to gas within the liquid and at the surface. In German, we talk about a Seidepunkt. In English, it's called the boiling point. When does vaporization happen for water? At what temperature? When does water vaporize, at least at normal room conditions? See if somebody knows. What temperature? What about Phil? What temperature does water vaporize at? Because water can evaporate at any temperature. It doesn't have to be this temperature. When does it vaporize? Good, I got one person knows. Let's see if another couple. Takes a little while sometimes for your responses to get to me. So H2O, water, at, yeah, Marino has it at 100 degrees C. That's why they picked 100 degrees, by the way, because it's the boiling point for water. So water does, and now all your responses are coming in. Sometimes they all pile up out there in the internet, okay? Good. So at 100, I get this thing called vaporization, which is different than verdunsten, which is the evaporation at a puddle, okay? However, vaporization is also a process. Vaporization is also a process. I want you to use a new word. Vaporization is also a process. Can you fill in the blank? And I'm going to tip that so you can see, by the way. So what sort of process is vaporization? You guys still out there? Someone ought to get this. Maybe your answers are still waiting out there in the virtual world somewhere. Sometimes that takes a while until I receive them. And there's one already. Marina, you must have a quick connection because I'm getting your answers first. That or you're quick on the draw, one or the other. Yeah, so like verdunsten or evaporation, vaporization is also endothermic. That's why if I'm boiling something in the kitchen, let's pretend I'm at the kitchen, I'd have to have this on a burner, wouldn't I? If I'm in the lab, there, Lisa's got it as well. If I'm in the lab, I'd have to have a Bunsen burner to do it, like we used one time in our class. Okay? So I need some sort of little flame there to make it happen. Oh, no, everybody's got it. Good. That's fine. Okay. Are we good? Okay. I want to talk to you now about an application of this, other than blowing like on your hand. All right. Well, that's not boiling, but okay. I got to erase a bit. The application is something where we use it in technology. As a teacher, I always have two goals, okay? One is I want you to know the chemistry and physics, and the other is I want you to know how it's used, either in nature or in technology. So we're going to look at something in technology. It's something that you have at home. I think everybody has. It's in this room called the kitchen. And it keeps things cold. And you can guess what I'm talking about. I hope. Now I'm going to put this up right here now, and we're going to what if I can use the other side? Oh, no, that's silver. Never mind. Just my own little experiment. That did not work out. Okay. The fridge. Thank you, UCN. So that's okay, UCN. You got it. All right, so here we go. Let's see. So my question's going to be, and I think we got just enough time for it, is how does your fridge work? How does a refrigerator work? How does a refrigerator work? Well, son of a gun, it has to do with exactly some of the stuff we're talking about. That's why I wanted to mention it to you today. Now, this whiteboard is not that big. I can't draw a whole big refrigerator or freezer, but I'll try and draw the important parts. Okay, here we go. Go big or go home. Okay, so here we go. Here's the fridge. Here's the front. And there's the back. Okay. So there's like the door and stuff, okay? Little handle. Just so you know what you're looking at. Okay. If you've looked in your fridge or freezer, if you look in the back, there's some like pipes, some little tubes back there in the freezer too. These little tubes, I'll just put them in here. And I can't draw a bunch of them because I don't have that much room. Let's just put one here. But if you look, you'll see more than one. And then they come out here. And here they go through some other stuff. We'll see what that is in a little bit. You'll see that in the back if you do that. And then down here, we got this thing which is called a pump. Sometimes if your fridge is a little older, the pump is louder and you might hear it come on. Or if you have the fridge open for a while and you close it, then usually the pump starts to come on. And if you listen, you can hear your refrigerator running. That's the pump. We're going to see what that does. Well, it connects here to this tube. Well, a pump squeezes particles together. So here they are. In here, it's a gas. Let me just think about it. And what the pump does, I'm just making sure you can see this enough, okay? That's what I've drawn so far. I'll tip the board so you can see it. Okay, the pump, it squeezes the particles together and changes them from a gas into a So I'll say the pump. Well, what it really increases is the pressure. I might as well be scientific about it. Increases pressure to change the gas to a See if anybody has a guess come flying in. So if I squeeze the gas together, it becomes what phase? I'm not changing the temperature, I'm just squeezing the molecules together. Now they're far apart, now I'm going to push them together, and they become the phase known as, starts with an L, rhymes with liquid. That's right, liquid. And you might say, why? Okay, well, let's see. Let's say I put in some food here. I put in a box of food and it's still warm. Here's some food. So I put in a box of warm food on the shelf, okay? The secret is really what's inside this thing. To change your gas to liquid. I gotta tell you what the fluid in this tube here. The fluid in the tube, it's not water. It's called a coolant. So now I've got the coolant over on this side as a liquid. Here, I'll put L here. Liquid. And you ready? Now comes the important part. Okay, the important part. What happens to the liquid when it gets close to the warm food up here? I know it's not touching the liquid directly, but it's getting something from the food. Well, it's getting from something. What's happening to the liquid right up here as it's getting close to this warm food? See if you can guess. I'll write some of this on the side too. And while I'm waiting, I'm going to tip that so you can see it. What happens to the liquid or the coolant, I should say the liquid coolant, as it goes up? Here, let's put some arrows. Here it goes down, here it's going up. What happens to liquid when it gets up by the warm food? What will it do? Emelina has it. Well done, Emelina. You're on your game today. So it turns back into a gas. That's right. So right up here, I know I don't have a lot of room, but I'm going to say it's going to be liquid goes to gas. But we said earlier today, now you'll see why I'm talking about this. We said earlier today that if liquid becomes a gas, it's endothermic, isn't it? It's got to take heat. Well, where's the heat coming from to change the liquid to the gas? Where's the heat coming from to change the liquid coolant into a gaseous coolant inside this pipe here? Where's that heat coming from? So I'm talking right in here. I got my liquid coolant, and here it becomes a gas. Why? It's endothermic. Where's the energy coming from? Right there to turn it into a gas. Ah, Lisa's got it. So does Marino. From the food. Yeah. So that's how it cools your food. It takes the heat from the food. Isn't that cool? So when the heat is taken from the food gets colder. Same in the freezer. Okay, if I have a freezer at the top, it works exactly the same way, just more extremely. Isn't that cool? So the heat is coming from the food. Exactly. Okay, so I'm so excited. I don't know what to write. Okay, let's write over here. I don't have room over there, so I'm going to say I'm put a little star. And my little star is going to be right here. And I'm going to say, can you read that? Yeah, you can. I'm going to say, hey, the heat from the food is used to change the liquid to a gaseous coolant, thereby cooling the food. And that, my friends, is how your fridge works. So let me tip that so you can see a little bit. And I want to see if you have some questions too. Like when I ask this to like students that don't know, they say, oh, the refrigerator, it adds coldness. Well, that's a bunch of crap. The refrigerator doesn't add coldness. It takes heat away from your food, doesn't it? It takes heat away here. And by the way, when it gets over this side in the back of the fridge, if you turn the fridge around and look, it has some really thin lines. And the thin areas are where the gas can give off heat. So back here, the gas is giving off heat and it cools down a little bit. But even here, then the pump has to like pump it down and compress it so it becomes a liquid again to go out back into the refrigerator. So the refrigerator is really, you ready? Really cool, isn't it? Sorry. Questions from you about how your refrigerator works? I'm sorry, Emelina, to hear that, but your connection, you're participating well anyway, which I appreciate. So questions from you about how your fridge works now. I want you to open it before you eat something, and I want you to look for one or more tubes in the back. And then if you can stick your head around the back of the fridge, I want you to look back here and see where the gas is giving off some warmth. And if you put your hand back there, if you can, you'll find that that's warm. That's warm. Okay, and then down here, the pump, when the pump comes on, you can open up the fridge a little bit and then close it. And then the pump comes on and we'll turn it back into a liquid again. So I hope you think that's neat. I think it's neat. And it's a great version of what we just learned. Okay. I hope your internet problems are not from me, but that's the way it goes. By the way, we say that the pump condenses the liquid before you go. So condensation or condenses. I think we had that word, but if not, so condense to go from a gas to a liquid. So it condenses the liquid. Beautiful other word for physics. Thanks, Emily, and I think so too. Thanks, everybody, for joining me. Maybe I'll see you at school someday. I hope so. Have a good rest of your day, folks. Bye-bye.